Okay, so this is lecture 15. So I'm going to continue the introduction to discrete time Markov chains by giving you an example of a discrete time Markov chain in this lecture. Okay, so from last time, remember that I gave you the definition of a discrete time Markov chain. So basically the discrete time means it has that discrete counting set. So here the counting set's not continuous, but instead you have n going from 0, 1, 2, etc., and you talk about these random variables x, n. And so the neat thing about Markov chains is they satisfy this Markov property. Basically what the Markov property says is that if you're looking at if at state xn, at present time you're in state I, that the probability of being in state j at the next time doesn't depend upon all of these previous times, but it only depends on the present state. So it's the memoryist property. The past isn't important, only the present influences what happens in the future. Okay, so we also introduced this notation of this one-step transition probability. So what is the probability that if you're in step I at this time step that you'll be in step j at the next time step? And here we have this is denoted by pji, not pij. So remember I told you to be careful because some probability books and stochastic processes books actually do denote this as pij and not pji. So here we're thinking about going from step I to state j. And what is the probability that that's going to happen? So this is what's called the one-step transition probability. Okay, so here's our example. You have a certain ice cream company, we're just going to call it brand A, controls 10% of the ice cream market, and they want to boost their sales, and so they start this aggressive advertising campaign. So they go out and they hire a market research company to analyze the potential effects of introducing this ad campaign and how is it going to affect them after a couple months of advertising. So the market research company that determines that if they go with this advertising campaign, they can expect the following. So this is where your probabilities come into play. So here they expect that with this advertising campaign that someone eating brand A ice cream is going to stay with brand A ice cream with a probability of 80% once you start this advertising campaign. And someone not eating brand A ice cream, so any other ice cream brand, we're just going to call it not brand A, will switch to brand A with the probability of 60%. So those with brand A are likely to stay with brand A with a probability of 80%. Those not with brand A are likely to switch to brand A with a probability of 60%. So let's assume that each family buys ice cream once a month. I don't know how often your family eats ice cream. That might be about right for some families. Maybe some families eat more, some families eat less. But we're going to assume for now that each family buys ice cream once a month. So we want to know after 1 month, how much of the market share can the company selling brand A expect to have? So remember, at the beginning, brand A controls 10%, which means 90% is controlled by somebody other than brand A. So what they're wondering is after 1 month of this advertising campaign, how much of the market share can they expect to have? Hopefully it goes up from this 10%. That's what they're hoping because that's where they're putting their money in. Okay, so here we're going to assume that there are two states. We have a state A and a state A prime. So A is going to be standing for ice cream brand A, and A prime is going to be any ice cream that's not brand A. Okay, so what we had is we had this scenario where we had if somebody's eating brand A, they're likely to stay with brand A with a probability of 80%. They're not eating brand A, then this advertising campaign is going to make them think and go, hey, maybe I should switch over to brand A. And they have a probability of switching of about 60%. So what's really nice to do is to draw transition diagrams. So a lot of modeling, and remember from like in the very, very first lectures that I showed you, lots of times I showed you schematics. And so before I even gave you the differential equation, I showed you schematics. So with all of these, and even with like the homework assignments that you're going to get, you really want to draw schematics. So what is it that is happening? So this is going to be called a transition diagram when you're talking about discrete time Markov chains. And actually, Continuous time Markov chains to some degree also. So transition diagram. So here we draw our two states. So we have state A and state A prime. And if we had had more, then we would have drawn more states. So here we only have two states in our system, A and A prime. And what we're given is that if you're in A, here you have an 80% probability of staying in A. So if you're in A, the likelihood is that next time you buy ice cream, you're going to stay with A. What's that mean? Is that if you're in A and you have an 80% probability of staying with A, then you have a 20% probability of switching to another brand. Okay, so what else do we know here? We know the people that aren't eating brand A, so these people over here, are likely to switch with a probability of 60%. So if you're not in brand A after this advertising campaign, you're likely to move to state A with a probability of 60%. So what's that mean? Well, the other 40% are going to stay with A prime. So there you have the other state staying with A prime. Okay, so now we have our transition diagram. We can actually do a probability transition matrix associated with this. So remember, this is our state diagram. So what you do to do the probability transition matrix is you think about your current state being your columns, and where that current state is going to go, this is your next state is your rows, sorry. So current state's columns, next state's row. So what's the probability that if I'm in A, I'm going to go to A? So if I'm in A and I'm going to go to A, that's 80%. What's the probability that I'm in A and I'm going to go to A prime? So here I'm in A, but my next state is going to be A prime, so that's 20%. Here I'm in A prime. What's the probability I'm going to go to A? It's 60%, so that's this part. Here my current state's A prime. What's the probability that I'm going to stay in A prime? Probability I'm going to stay here is 40%. So these probability transition matrices, the way that we've written them, in having the current state here as your columns and the next state as your rows, then each of these columns should sum to 1. So here 0.8 plus 0.2 gives me 1. 0.6 plus 0.4 also gives me 1. So in other books, they're written with current state over here and the next state here. And so in that case, the rows sum to 1. So just make sure if you're reading some other article or some other paper that you have the correct notation and that you understand the way they're using the probability transition matrix versus the way we're doing in this class, the way that Linda Allen's book does it. So again, here we have the current state across the columns, the next state across the rows, and the columns should all sum to 1. Okay, so now we wanted to answer that question, what's going to happen in 1 month, right? So let's make our initial state. So our initial state, how many were in brand A, how many people ate brand A ice cream, where they only had 10% of the market, which meant that the other 90% was someplace else. So this is our initial state. Okay, so what's going to happen in 1 month? Well, here's 10% of the market is with A, 90% of the market was with A prime. So what's going to happen is if you're up here with A, 80% chance you're going to stay with A, 20% chance A prime. So this is just like in our transition diagram, right? If you're in A prime, there's 60% chance of going to A, 40% chance of going to A prime. So after 1 month, what's the likelihood? What percent of the market should state A have, assuming that they were right in these probabilities, assuming that the research company was right in that 80% and 20% were about right, and 60 and 40% were about right. So then what share of the market should state A see? Should it still be 10%? Should it go up? Should it go down? Well, obviously we want it to go up, right? So here, what's the probability someone uses brand A after 1 month? Well, there's a couple of ways of getting there. So here, if they started with brand A, 10% started with brand A, then the way that they stay with brand A is through this 80% still stay there. What's the other way of being in brand A at the end of 1 month? Well, they could have started over here, right? They could have started in this 90% that used something else, that bought different ice cream. And then there's a 60% chance of all these that were in here going to brand A. So at the end, after 1 month, we expect to have, well, you start with 10% already here, then 80% of those are going to stay. So those are some people that we get. We had 90% in A prime, but we expect 60% of those to switch over to brand A, so we also have those people will be in brand A at the end of 1 month. So we expect after 1 month to have about 62% of the market share using brand A ice cream. I think it's a little ambitious to think after 1 month that campaign is going to do that well, but this is what the research company in this example problem said. So like I just said, the probability after 1 month of using the advertising campaign, we expect 62% of the market share to belong to brand A. So here we can say this is the next state, so this is S1. We just denote the next state, S1, so we expect 62%. While 62% is using brand A, then 38% is not. Okay, so we can actually use the probability transition matrix to actually come up with this next state. So how do you do that? Well, here, to get to the next state, S1, all you have to do is take the probability transition matrix and multiply it by the current state, and this gives you what state you expect to have next. So now what happens after 2 months? Well, again, if this is S1, then what I can do to figure out what's going to happen next is I can take the probability transition matrix and just multiply it by S1 here. So here my probability transition matrix times by S1. After 2 months, I expect maybe about 72% to be using brand A, and then only, around 28% not to be using brand A. So the way I can actually write this is my second state, my state after 2 months is the way we're thinking about this. The state after 2 months, well, S1 was just P times S0, so I can rewrite this as P times S1 was P S0, so this is really P squared. So you kind of get it after 2 months, I have this P squared here. So we can kind of think of what we can do after 3 months. Yes, we have a P cubed times our initial distribution, and we can figure out what's happening. And if you keep looking at this, what's it look like? It looks like these numbers are starting to stabilize. They're starting to they're not going up as quickly. And so you can guess that it's approaching what's called steady state. And if we look at it, the steady state of this system, which we'll actually be analyzing later in this course, is actually 75% of the market would be using brand A and 25% would not be. The steady state basically means that if I take my probability transition matrix and multiply it by my steady state basically means that there's no change. So if I take this, P, multiply it by my steady state vector, I get back that vector. So steady state means it does not change. And this steady state is actually an eigenvector of my matrix P. So remember from linear algebra eigenvectors? So it's an eigenvector associated with eigenvalue 1. Okay, so with MATLAB, you can do this. So with MATLAB, I have a code in MATLAB that is on D2L. It's called plot state. So plot state basically gives you have to input. So remember, this is a function. Here's a function. So in your command window, you would want to type plot state, and you want to give it an input n. N is how many months you want to look at, how many months you want to examine. So what's in here is your probability transition matrix. This is the one that we defined. We set up our initial value. So what this means is S of my first 2 rows and first column, my 2 rows and my first column is 10.1, 0.9. This just is going to print off a nice little table for us. So this is going to print off brand A, not brand A, and it's going to just keep updating. Oops, sorry. Let's go back. It's going to keep updating as a function of the months and how many months we are. So this prints off our initial. And then it plots the percent share through the n months. And so basically to find what the share is, you can take P to the I, however many months you're talking about, times your current state. And so then all this does is a way to print off, and you can do help f print f if you're interested in this notation, but this prints off This is a space saver to say I want to plot some numbers. What do I want to plot? Well, here I want to plot my number of months. Here I want to plot what's in brand A at that time. Here I want to plot what's not in brand A at that time. Okay, and so then this just gives you a figure. So this plots the trend across time, and it labels the axes. So if you run this, if I do plot state of 5, basically it starts out with 0. So at 0 we have our initial, and then we have at n equals 1. This is what we actually calculated already. We already did all of these, and so you see, if you look at the graph, it's approaching a steady state here. So here's my brand A, and here's my not brand A. Okay, so next time we're going to do another example of a discrete time Markov chain.